So this video covers a partial solution or somewhat of a complete solution in some ways you can say to the precept on week number 2. So one of the things that we needed to take more time to think about the mathematical models of runtime analysis. So for example, there are a few things that are very important. We avoid big O notation in this class, and we avoid the term complexity. Instead, we always talk about running time of an algorithm or order of growth if the constants don't matter, or the tilde notation if they do. So the two things that you would be very careful about using is the tilde notation, where the constants matter, but you keep only the larger order term, higher order term. Order of growth, you drop all the constants and you just talk about either n squared, n log n, and so on. So part A, this code, let's go over some of the ideas here. The key thing is there are 3 loops here. So one thing you should not do is to think that in the analysis, all we have to do is multiply m times n times n. That may not be correct. So you got to be careful about what you're going to do there. The question asks, count the number of array accesses made during the code execution using tilde notation. So this means that you can't just multiply, you have to get a precise count by looking at the code. First of all, it talks about the array accesses. So this means that we look at this statement and there are 2 array accesses, a's of j and a's of k, and that statement is going to be executed by these 3 loops. But if you look carefully further, you realize that this code here is really what is important for us to do first, and then we will worry about this outer loop. The reason I say that, because the loop condition, this statement that inside these loops, this statement only depends on j and k. So whatever you're doing, so if you start from inside and outside, so you sort of analyzing from the innermost loop to the outermost loop. So if you start from here, so you know that these 2 loops affect how many times this gets done. So how do we know that? I mean, again, you don't want to multiply n by n, because note that as the value of j changes, the number of times the ka loop runs also changes. Now, obviously, if you had a 0 here, then you don't have to worry about it. You can just multiply it. You know that. But because you have a j, whatever you do with the k depends on j. So how do we do that? So let's consider only the inner 2 loops first. Every execution of the if statement requires 2 array accesses, as shown here. The comparison is executed n-1 times when j equals 0. So if you assume j is 0, this is going to go from 1 to n-1. So it's going to be executed n-1 times when j equals 0. If j equals 1, it'll be executed n-2 times, and so on. And then only 1 time when j equals n-2. And 0 times when j equals n-1, because j equals n-1 would be the last j in this loop. So thus, the comparison is executed, the sum of those numbers, 0 to n-1. Now, I will leave that detail to you to find out using the arithmetic sums, because we know 1 to n would be n over 2n plus 1, but 1 to n-1 is going to be n times n-1 over 2. So one way to think about that is take the sum from 1 to n, which is n over 2n plus 1, subtract n from it to get the sum from 0 to 1 to n-1, which will give you this. So now, if you multiply that by 2, you're going to get this number. Why do I multiply by 2? Because I'm doing 2 array accesses, and this is how many times I will execute that statement. So I end up with n times n-1. So the order of growth for that piece, this part here, or the exact number of operations, is going to be n times n-1, the array accesses. And then if you consider the outer loop, Then we make exactly m iteration, and therefore we write this tilde notation m times n squared. Notice that you should not drop any constants, but in this case, because we multiplied the answer we got by 2, since we have to have 2 array accesses for each if statement, we drop the constant, so our constant is 1. So here's what we get as the tilde notation. So moving on to so that again the key idea here is that this sum, which you should look at the notes and try to figure out exactly how that works. The second part says that if it takes 100 seconds to execute the code fragment for n equals 1000, m equals 100, estimate the runtime for n equals million and m equals 1000. So in other words, we have to think about a model. So the model would be that we know that from the previous part, we know the number of things that code runs is proportional to mn squared. So we write it as a function tmn. Then we plug in the numbers that we know, like we plug in n equals 1000, m equals 100. So, and then we know that that's going to be 100 seconds, and on the right hand side, I plug in m equals 100 and n equals 1000. And then plug in the values where the writing time is unknown. So in this case, m equals 1000 and n equals 1 million. And then we have this side, mn squared would be m and n squared. If you divide the two equations one by the other, you could get the one where the time is unknown. And if you do the algebra, you will come up with 10 to the power 9. There are other ways to explain this, but I think this is a much cleaner way of doing it. The other way to think about this is that because it's mn squared, so if you double the n, your runtime will be multiplied by 4. And if you make the n 10 times that, then your runtime would be multiplied by 10 to the power 2. Okay, 10 squared, and so on. So that's the sort of the solution to the first one, and the solution to this 2a's is 10 to the 9. Now, in the optional case, the two things that we have to think about is that how would you, given these things here, how would you order them? So I ask you to think about these first. When we do analysis, usually we count the total operations required to execute a piece of code. The count is often given as a function of n. So suppose for some algorithm we came up with a count as 3n squared log n minus 2n. If smaller order terms are dominated by larger terms, so if you think about very large n, there's no reason to include this in any analysis. And therefore we say by tilde notation is 3n squared log n. Notice that we did not delete the constant. If you look at the order of growth notation, we're going to drop it and we call it n squared log n. And you should always know this, that constant time algorithms are better than log n algorithms, are better than linear algorithms and linear arithmetic algorithms and quadratic algorithms. So that's an important thing to know, because that'll help you order things. Another thing you may want to know is that this formula, I ask you to stop the video and make a note of this. In fact, there's a little typo here. It says that this relationship exists for n. This should be d and this should be c. If d is bigger than c, then the log base d is going to be less than log base d, c. So I will exchange these to c and d. So in order to order these three things that we've given to us, what we can do is you can think like this. You were given 2 log 3n and 3 log 2n. Really, the 3's and 2's don't count in the sense that it doesn't matter in analysis because they're constants. You can always convert one base to another base. So therefore, these two are really equivalent things. Whether you have something in front or not, in terms of the order of growth, this would be log n, both of these things. And clearly n squared is the largest of the thing. And then we know n log n is probably between less than n squared. But the only relationship that we have to derive from here is this one here. So here you can think of this as n to the 1/3 and n log n. According to this formula, if a is less than b, so if a is 1/3, b is 1, so that's what we use to conclude that the n to the third root is less than n log n. Now, you can conclude that the log functions are always smaller, so slower, the faster in terms of running time than any power of n, even irrational power of n. So you can take n to the the 100th root of n, that's still log n is better, and so on. So now let's think about part D of the problem. The part D says, what is the order of growth of the running time of the code fragment below as a function of n? So obviously it creates some kind of an input object, and it creates an array, and in fact this one is creating an input array based on some argument that's given to you, and then it reads some numbers into this integer array, and then it knows what the length of the array is. And then it calls unique count equals 0, and then it sorts the array, and then have an index I equals 0. So it's asking the order of growth. This means that we have to count how many times things are happening here in terms of n. Now, a naive way to think about this is to say that because it has two loops, while, and they are nested, you may think that the order of growth is n squared. But that may not be true. So you got to be very careful here. If you carefully read the code, it says, okay, let's make current the AI. We will add unique count to 1, and then we will start the j iteration from I plus 1. Then you go through the j iteration as long as it's less than n, or aj is not equal to the current. So notice that if aj is not current, then you break out of that while loop, or if you reach the end, you break out of the while loop. So until then, you're inside the while loop, and then you're incrementing j. And then when you come out of this inner while loop, you're going to set the I to j, and then start this process again. So the question is, how many times this thing actually runs? So you can suggest that the run algorithm on a small example, for example, if you have 1, 3, 4, 1, 4, so if you sort it, you would get 1, 1, 3, 4, 4. Right? That's what you're going to get from the array. This is the with value, so you sort it, you get 1, 1, 3, 4, 4. Now, if you look carefully into the code, what you will notice is that as long as AJ and current are the same, so that means this inner loop only runs through when the things are equal. Okay, so if you have 1, 1, or 3, and 4, 4, I guess the 1, 1 would run, they are equal, and 4, 4 would run. So the inner loop actually processed the unique elements. So it's 1, and then 4, and then the 3 is only one time here. So if you look at this code here, all it does is that if you really carefully look at it, the trick in this question is that the I and j are in effect the same variable. So that's why we don't multiply it, and therefore both loops only run linear number of times, n. So the cost is dominated by the runtime of the array sorting. So the overall code is n log n. We know the array sort would be n log n, the best sorting. And these two loops only do n things. Okay, so it's not n squared, it is n, because really this code is doing is to look for unique things. Like if you have this array, the unique things are 1, 3, and 4. So it's finding how many unique things are in an array where possibly there are duplicates. Okay, so that's one of the ways to think about that code.